Hello, this is James Diamond with GlockCNC, and in this video we will be talking about spindles and what goes into them. Why are they kind of tough to make really, and why do some of those brands cost so much, like Fisher or GMN, where you might be spending $20,000 pretty easily, maybe even $40,000 on a spindle, and one that might not really seem that complex to you. So let's dig into it and start talking about the different areas of the spindle that really can make it kind of tricky to make, because some of it, as you probably know, that in the past I had a manufacturer, actually it was two different manufacturers who were making spindles for us, and some of them messed them up for like 4 times. And even that last fourth batch, there was some of those that came in good and there's other ones we couldn't even use. So why is it so tough? Let's talk about it. So, and if we're looking at this spindle, we have a couple areas. The area here where bearing sets, and an area here are bearing sets. And actually, let me go on the screen here to our BT30 so you can see an example of that. So, bearing set, those bearings set right here, and this bearing sets right back here. Okay. That diameter is what's called oversized, or it's an interference fit with the bearing itself. Now, I should have probably grabbed the right bearing for this, but it's what I have right now. So let's talk about interference fit. I know probably a lot of you know what that is or shrink fit is, but some are newer, so we'll talk about it just real quickly. So let's say this is the area where the bearing needs to fit, and this is the bearing I'm using on there. So if it's interference fit, this diameter is going to be slightly larger than the inside diameter of this bearing, so it's going to interfere, and you could just, if you're trying to put it on as it is, it would only get to right here. So in order to get this to fit and fit tightly, what I'll do is I'll use an induction heater and I heat up the inside of this bearing, and once it gets sufficiently large from expansion, it will now fit onto this bearing area of the spindle, and then as it cools, it shrinks to the size of the spindle, and it's really on there really good. So it's the same with this front part. So that's when I talk about shrink fit or interference fit, that's what I'm talking about. Now, there's some tricky bits to that, okay? So this diameter and this diameter, depending on what bearing I'm using, whether it's an ABEC 5 bearing, an ABEC 7 bearing, or an ABEC 9 bearing, which are all different accuracy levels of bearings. I have a completely different video on bearings if you want to watch that. They all have different recommendations from the factory of how much range of diameter this can be before it's either oversized or undersized. Now, you don't want to undersize, you don't want to be able to just slide this thing on, because once this heats up, this, because it's a thicker steel compared to the steel in this, they're going to heat up and expand at different rates. The inside of this is going to expand more quickly than this thick steel portion right here. Once that happens, that means this can slide actually, or just going to wobble around in there, and that's a problem, because now you introduce run out, and whatever, if it's a lathe, whatever you're trying to turn, that material is wobbling. If it's a mill, your cutter is now wobbling, right? Makes sense? So this can't fit in there too loosely. That's why you don't want to slip fit in there, and this has to be a shrink fit, but it has to be a sufficient shrink fit that once this heats up, it's not now going to become loose. However, it can't fit on there so tightly that it puts way too much pressure on the balls on the inside of this bearing. It's just expanding it so much, it's pushing it out, which is then pushing on the outside of this, and then that's pushing on the area where it goes in the headstock. So it's all kind of crushing it. And to give you an idea, an ABEC, let's say an ABEC 9 bearing, you're talking 1 micron is the variance that is allowed in the diameter of the shrink fit for this. Not much. And it gets a little easier, but not by much. With the ABEC 7, they give 2 microns with some of the manufacturers. Some will give you a little more leniency, others do not, depending on which brand you're buying. But that gives you an idea of just how close in tolerance this area has to be, and that's actually really hard to do. And so these have to be sent out to be ground, not just put on a lathe, turn down, where you can finally fit a bearing on there and call it good. It really doesn't work that way. If this is oversized, let's say by I'm going to say, I think if I remember correctly off from the specs, one of the bearing sheets, if it's oversized by, let's say, uh, 2/10, I believe it was the example they gave, it can add an extra 188 pounds of outside pressure to the inside of this, and that's pushing everything. So having it oversized is a problem. But again, you can't have it undersized because then this thing will, the spindle will slide back and forth in the bearings. And even if you have it captured with a nut so it's not sliding back and forth in the bearings, it can wobble up and down inside the bearing because this thing is expanding on all sides. If it's expanding on all sides, that leaves room all the way around it. Hopefully that makes sense. So it gets even a little more complex than that though. So this area has to remain concentric to whatever the taper is in here by a very finite amount, and they have to be concentric with the back. You can't have this back area here, let's see if I can point at it right. You can't have the back area here out of round, not straight with it, because that will put like a lever on this and it will cause the front end to wobble. So this all has to be just right and to a very finite degree, especially when somebody, let's say, is in an R&D lab or maybe even a watchmaker. They might want to use ABEC 7, ABEC 9 bearings, and then when we get those orders in, we measure these to find the ones that fit within that parameter to be able to get the accuracy that they want. Even though this will be a secondary grind on the inside for some of those, this still has to be right, because if it's not, then we have an energy management problem. So if this is pushing too hard on the outside, this is expanded too much from shrinking on an oversized spindle, then it's going to put extra pressure on the balls in here, and the extra pressure on those balls creates more friction. More friction is going to create more heat, and that can eventually ruin a bearing, and it can have other side effects as far as how things fit even inside the headstock. So there has to be a real balance in there of how tight this needs to be on there so that it's not wobbling in there or it's not actually sliding in there. But here's another level of challenge when it comes to now turning this into a unit with a headstock. Bearing manufacturers will also have a specification for the size of the hole that bearing can actually fit in. Now, it makes it even more complex when you're using two dissimilar metals. In this case, we're using aluminum, and this is primarily, well, all of this is steel with the exception of the grease inside of it. Which means that as it heats up, they are going to expand at different rates. That means if this is just a slip fit, or even the shrink fit is not shrink fitty enough, if that's a word we can use, that means once it heats up, it can wobble around. The whole assembly can wobble around in there. So it has to be sufficiently tight. Once we heat this headstock up, slide the whole assembly in there, it has to be sufficiently tight that it'll hold it in under heat, but not so tight that it becomes problematic. Now, bearings are different, and there's a whole different video on bearings. In a deep groove bearing, this will always, because of those different factors and how tight it has to remain on the spindle and inside the headstock, it will always run warm, especially when the break-in period is happening, which can be a long time. This can run hot for a while. However, after a while, it should actually begin to run more cool, but it will always run warm when you're running higher speeds with a deep groove bearing. It's a little better off if you're using, I shouldn't say a little better, oftentimes it's a lot better off if you're using angular contact bearings, and a whole lot better off if you're using angular contact bearings with ceramic balls in them. But again, that goes into a separate video. So you can see that there are a lot of different factors that come into place and why it can become so difficult to manufacture these spindles from the aspect of design and actually the dimensions that this is being made at. The other significant challenge to this comes with how they are being manufactured and the equipment that's being used to manufacture the spindle. Basically, in a nutshell, you can only build a part as good as your machine is going to allow. And not all machines can just do everything. A turning center is not going to give you the same level. It'll give you excellent accuracy, but it's not quite the same level as grinding. So these surfaces have to be sent out. Once it's turned, they have to be sent out and ground. And this may be a back and forth procedure. This might go, the rough area might get finished, and as far as these bearing areas, then these bearing areas get ground, and it goes back to the shop to get the inside turned. However, it has to be done to get this done in such a way that they can get the accuracy not just once but over and over again. So that's what contributes to the complexity, among other things, I suppose. The complexity of getting a spindle made and made properly according to the specifications that are required by the bearing manufacturer, and to get the whole thing to just work correctly. That gives you an idea of it. So when you're thinking of this, we have a lot of people who have come from looking at other manufacturers of spindles that they might be looking at a spindle. They're all starting around $15,000, $20,000 for what they need for a custom application. And they might find, let's say, our BT30 or an ER that we offer, and they're shocked how inexpensive it is compared to what they've been finding, because it costs so much to make these. And of course, those bigger companies have a lot more overhead. That even being said, I'm sure with the cost of everything going up and the cost of bearings going up for us, at some point, even us, we'll probably have to move these up, because that precision costs quite a bit of money, to the point where some of you who might take a look at grinding, it's been set as a rule of thumb with grinding, for every 1/10,000th that you want to gain in accuracy, it can raise the cost of that job by a factor of 4. So a lot goes into it, and now you know a little more about manufacturing spindles and their complexities.